Applications of linear systems. The first application, I want to talk about curve fitting. So let's look at an example. This first example is a question. It is a question regarding a line. Do we have such a line that will pass through the given points? Now we are given 3 points. So the first one, you see each point is an ordered pair. That means it is a point in the R2. Yeah, so we have x, y coordinates of a point. So that's 1 point, another one, 2, 7. It's another point, and then -3, -1. So we have 3 points. We know that it's always possible if you have 2 distinct points, we can always draw a line. So, but given 3 points, is there a straight line that passes through all 3 points? So that's the question. We need to write the expression of a line. So what is the general expression of a straight line? So we can write, for example, in this form, ax plus by equals c. However, we don't know yet the value abc, because if we know the value for a, b, and c, so then we can know the line, right? So the straight line will be known. But right now we don't know, but we want to choose, we want to see whether it's possible to find numbers for a, b, and c, such that this straight line equation will pass through all 3 points. In other words, if I put 1 for x, 7, yeah, I replace x with 1, replace y with 7, then 1, 7 should be a point of the equation. So let's say a times 1, b times 7 equals c. So ABC should be so such values that this equation will pass through the first point. For the same reason, we can require the equation, we can require the second point, which is 2 and 9. X is 2, y, when the y value is 9, it will satisfy the equation as well, because this line, we hope such a line will pass through the second point. And this same line will pass through the third point. That means when x is -3, when y is -1. So this is the system. So each equation is because that condition, that the line will pass through a point, right? So when the line passes through the first point, we get the first equation. When the line passes through the second point, we get the second equation. And then third equation, if the line passes through a third point. So if the line passes through all 3 points, we have a system of 3 equations. But do we have a solution for the system? If we can find ABC so that all 3 equations are true, then that means we have a line, right? So that means the question is actually about existence of a solution or not for the system. So let's solve it using augmented matrix, because we quickly write the augmented matrix because the unknown variables are ABC, the coefficient matrix. By the way, because ABC are the unknown variables in the system, so we want to write the system in the standard form. Standard form, that means we can put A times 1, which is still A, B times 7, and C, we can move the C, we can subtract the C from both sides of the equation, first equation. So we get 0. So you can see clearly the first equation is an equation of 3 variables. Second equation, can write 2A plus 9B, and then we can minus C. Then we have a second equation. It's another equation of 3 variables. And the third equation, negative 3A minus 1B minus C equals 0. So it's a homogeneous system, because once we write the system in this form, then we realize a 0 vector on the right-hand side. The left-hand side will be the combination of the variables. So it's a homogeneous system. Solve the system is not difficult. We have, used the reduced echelon form many times. Let's practice this again with the system. So here is the augmented matrix. 1, 7, negative 1, and 0. And then 2, 9. Okay, that's a 9. 2, 9, negative 1, 0. Negative 3, negative 1, negative 1, 0. So this is the augmented matrix. And then we work with the matrix until we reduce it to the reduced echelon form. So as we know that we want to replace the second rule. So here is the first time we keep the first rule as is. And then we want to replace the second rule. Okay, so what we can do is the rule 1, we need to multiply a number, right? This is the number. So a multiple of rule 1 will be added to rule 2. And this way we replace the second rule. So negative 1 times first rule is being added to the second rule. Then we get a 0. And negative 1, negative 2, you see negative 2 times the first rule, which is negative 14. Okay, times that, negative 14, add 9 will be negative 5. And so this multiple, then negative 2 times negative 1, which is positive 2, add negative 1 is 1. Okay, that's a replacement. Replacement of the second rule. And then now replacement of the third rule. So the next replacement is a multiple of the first rule. What multiple? Because this time we want to make this entry 0. So that's clear that first rule times 3. So first rule times 3. Okay, this multiple of the first rule is being added to the third rule. So this way we can replace the third rule. So the third rule, after you add, you will get a 0 here. And then we can see the 3 times 7 is 21. 21 add -1 is 20. So get 20. And then we have, again, 3 times this is -3. Add this number is -4. So that's our current matrix after the replacement of the second row and replacement of the third row. And we need to continue. So because right now it is not yet reduced echelon form. To continue, we notice that we can see that this is a multiple of the second row, right? Third row is a multiple of the second, because if second row times 4 is added to the third row, then we can get a row of zeros. So let's do that, because right now we recognize so that's the pivot. We're done with the first column. Then the next pivot element is this. So we can use it. What we do is that just keep the first row as is. Second row, and we can also just for now, let's keep it as is. We want to use multiple of the second row. So, and so what do we do? It's the second row times 4. A multiple of the second row will be added to the third row. So now it is a replacement of the R3, the third row. So you see, once you add this multiple of the second row to the third, you get a 0. So the 0 multiple added to 0 again. So then 4 times 1 is being added to -4. And we get a row of zeros. So that's for the reduced matrix. But now we still want to reduce by doing a scaling, because the second row, if we do a scaling, that means row 2 times or divide -5, right? So you can multiply -1/5. So let's say row 2 divide 5, -5. So that's a scaling. That means we keep everything else the same. So let's just keep everything else. First row, same as before. Third row is a row of zeros, same. And then the second row is a scaling. So each entry is divided by -5. Now we notice, right, this is the pivot. We want to use it. We want to use that to reduce more of the entry above it, because that's not the only non-zero entry in the second column. Look at the second column. So this one is fine, it's 0 now. But the one above it, above the pivot, is not yet 0. So that's 7, we hope to make it into 0. What do? We do another replacement. Replacement of the first row. So this time we are going to keep the second row, which is the row with the pivot, right, as is. The third row and first row will be replaced. So we replace the R1, first row, by what? A multiple of the second row. So the second row times -7 will be added to first row. Because of this replacement, the first row will become 1, 0, and then this number, as you can see, this number, -1/5, times -7. -1/5 times -7 is being added to the first row. That means add to the -1. You see we have a -1 here. What is the number? Number is 7/5 plus -1. So then we get 2/5. And this last column is always a column of 0. So you do not have to write the column of 0 as long as you remember for homogeneous system during the process of row reduction, that last column is always 0 column. So are we done? So if we check the first column, that's the only non-zero entry, the pivot 1 is the only non-zero entry. Second column, there's only 1. That's the only non-zero entry. So we got the reduced echelon form. With this reduced echelon form, we're ready to give a solution. So the solution, the first equation is now A, 1 times A plus 2/5 times C equals 0. And the second equation is 1 times B minus 1/5 times C equals 0. The third equation is just an identity. It is always true. So we can write 2 equations and solve for the ABC. So when we get a reduced echelon form, that's the best form we can expect. So now we're ready to solve it based on the reduced augmented matrix here. So the equivalent equation is this. So let's just write AB in terms of C, which is a free variable. So A is -2/5 C. B is 1/5 C. And C is anything. C is free. So if we have found a solution, A, B, and C, A, B are in terms of C. So now we can plug these values into our form. Recall that our form of the straight line is this, AX plus BY equals C, right? So we just now put into this form. So let's look at the equation we got here. So AX plus BY equals C. So now A is -2/5. That's the A. B is 1/5 in terms of C. AX plus BY equals C. So A and B are both in terms of C. And now we see that this C can be canceled, right? As long as the C is not 0, then we can rewrite the equation. So for example, we can divide C, both sides of the equation. We can write as 2/5 after we can divide C, both sides, 1/5 times Y equals 1. Okay, I just canceled. Divide the C. So we get this equation. And also, if you want to make it even a better looking equation, if you do not like the fraction, we can multiply both sides of the equation by 5. So if left side times 5 is -2x times 5. 5 times 1/5 is 1 times y. 1 times 5 is 5. So yeah, this straight line equation is same as this, right? They're equivalent. So we finally found a line this is the equation of the line. This is the equation of the line that will pass through all 3 points, given points. So yeah, there exists an equation or a certain line that will pass through all 3 points for this given set of 3 points. If you think back, look at the 3 points again. So as we are given the 3 points, recall that they are 1, 7, 2, 9, and -3, -1. These are the 3 points that are given. And we try to determine, right, whether there is a line that will pass through all 3 points. So if any 2 distinct points, the answer is yes, for sure. But if 3 given points, then we don't know. But after the curve fitting, so if we require a line pass through the 3 points, we got a system to solve. Do we have a solution for the system? So it became a matter of deciding for the system whether there is a solution. So we found that there is indeed a solution for the system. Let's think of an alternative way of solving this. As we remember that, so here, let's think of another way. Of solving the same problem. So we're still looking for a line that will pass through all the 3 points, the 3 given points. But notice that we are actually looking for a line. We can write the line in the slope-intercept form if in case you feel more familiar with the slope-intercept form. We can assume it, the straight line equation is in this form. So what we're trying to determine is the slope and y-intercept. So these 2 are the values. You see, this time we have 2 unknowns. We want to decide whether we can find possibly slope and intercept for a line such that this line will pass through all 3 points. So in the previous case, we used the general case because that equation, the form we used was this form, ax plus by equals c. Notice this is a more general form because this can include the case when the line is vertical. That means when a slope of the line does not exist, right? So this one include that case because you see when the line is vertical, that means the x okay, for example, this b will be 0. So this term will be gone. So x will be equal to some constant. So this the solution of this form includes all possible situations, vertical or non-vertical lines. So we assume that that's a very general straight line equation. However, this form, right now I'm proposing, it is with the assumption that the line is not vertical, right? Because we assume there's a slope. Because when a line is vertical, then slope does not exist. So when you assume this form, you already assumed there is a slope. It's not a vertical line. But for the given set of 3 points, it is still possible. Let's look at the 3 points. The x coordinates are not the same. right? So if you look at the first point, x is 1. So if I pick 1, 7, so it's somewhere, x is 1. Second point, x is 2, 9. So 2, 9, for example, here. So already we see that if you're deciding whether a line will pass through the 2 points, it cannot be a vertical line, right? Because in order for 2 points to be on the same line, then the x coordinates of the points must be the same so that they can be on the vertical line. So yeah, so we should not be concerned if we use this equation, slope y-intercept form, for the given points. So the given points cannot possibly stay on a vertical line because their x coordinates are different. Okay, so now we assume such a line in slope-intercept form. Do we have such a line that will pass through all 3 points? So let's require this line will pass through all 3 points, see if we have a solution to the system. So first, when x is 1, y should be 7, right? So when x is 1, y is 7. That's the first equation. When x is 2, y is 9. Then when x is -3, y is -1. So we have a system. We have a system of 3 equations, and we try to determine the slope and the y-intercept. So can we possibly solve this system? That means can we determine a solution for the system? So let's write this system. The first equation is m times 1. That means 1 times m plus b equals 7. So this time I want to put 7 on the other side. The second equation is 2m plus b equals 9. And the third equation is -3m plus b equals -1. So I have 3 equations and 2 variables, slope, y-intercept of the line. So we want you see each equation means the line passes through the first point, the line passes through the second point, and the third point is also on the line. So we have 3 equations. So 3 constraints, and then for the slope and y-intercept to satisfy. So if we solve this time, you see it's a different setup, right? We're looking for a slope-intercept form. But this time we got a non-homogeneous system. So this is not a homogeneous like last time. Last time we had homogeneous 3 unknown variables in a system of 3 equations. This time we got 2 unknown, but still, 3 systems. So let's solve it. So again, use the augmented matrix. Use augmented matrix, which is 1, 1, 7, 2, 1, 9, -3, 1, -1. Yeah, so then we reduce. So first we keep this is the pivot, right? We keep the rule, first rule, and then do the replacement of the second rule. So we use multiple of the first rule, so to reduce this number 2 here in the second rule. We want it to make it 0. So immediately we know the first rule times -2 will be, that multiple of first rule will be added to the second rule. So then -2 times first rule is being added to the second rule. That's a replacement of the second rule. So we get, and then third rule, we also need a replacement because as you can see this, you want to make it 0. So the first rule, the multiple of the first rule must be a 3. This multiple of the first rule adds to the third rule. So it's a replacement of the third rule. And then, so the third rule now becomes and now we can do a scaling. Because in order to get the reduced echelon form, we want to make this is the next pivot element. So we can make it into 1. That means the second rule will be multiplied by -1. So this is a scaling operation. So second rule becomes, okay, every element times -1. And now, you see, if you keep everything else as is, so this one step is just do a scaling. And then now after we scale the second rule, we're ready to use it. Use the second rule. This is the rule with the pivot. So multiple of the second rule will be added to the first rule. So in order to make this element 0, right? So this one I want to make it 0. So replacement of the first rule. So that will be replacement. So this is the second rule times -1 add to the first rule. So that's a replacement of the first rule. Keep the second rule as is, and then add multiple of the second rule to the first rule, and we get a 0. So we get a 2. And again, at the same time, we also want to make this 4 a 0, right? Replacement of the third rule using the second rule. So the second rule times -4 add to the third. That's a replacement of the third rule. So we get 0. And when this 5 times -4, you get -20. Adding to 20, we get 0 as well. So now reduced. You just double check. So this is the pivot and pivot. So, and those 1s are the only non-zero in the column it's in. So we have got a reduced echelon form. So what does that mean? That means the first equation is m equals 2. The second equation, that is the variable b, right? 1 times b equals 5. As we know the equation, you see the first variable is m, second variable is b. So we have 3 equations for 2 variables. And after reduction, we notice essentially there are 2 constraints, and we can immediately solve. This reduced echelon form means that the first equation is now reduced to have only m variable, m equals 2. The second equation has only the b variable, b is 5. So the solution is evident, right? We found that m is 2, b is 5. Then what is the equation of the line? Equation is slope, which is 2x plus b, which is 5. So we have found a straight line that passes through all three given points. Because this is an alternative approach. But is this the same line? So if you go back to the first approach, what we got, it is the same, right? So if we see that that's the first approach when we use it, when we look for ax plus by equals c, we found ABC. A and B are in terms of the C. And we got a solution. Although it seems like C is a free variable, you feel maybe we have many solutions, but actually after we cancel the C, there is one unique line that will pass through all points. We can cancel C because C has to be non-zero. Because if C is a 0, what happens? If C is 0, then that is not a straight line equation, right? It is just a 0 on left side, 0 on the right-hand side. Then, yeah, that's not a straight line equation. So C has to be non-zero. And hence, we found a unique solution of this form, which is this equation is really the same as y equals 2x plus 5 in slope y-intercept form. So 2x plus 5. So this is the solution if we used another second approach, we got the same, 2x plus 5. So both approaches, well, ended up with the same line, which is not surprising. So we have a unique solution for the system, but the different formulation. So we assume that the line in different forms in the two methods.